Hi everyone, let's calculate the integral of arcsine of x divided by x from 0 to 1. To solve this integral, we need to go through several substitution methods and also use an integral identity. Let's start with that. Rewrite the arcsine of x as the integral of 1 over square root of 1 minus t squared, and we're integrating with respect to t. And the bounds are going to be from 0 to x. Now we can plug that into our integral. This results in a double integral and gives us the outer one is from 0 to 1, the inner one is from 0 to x. And then we have 1 over x times square root of 1 minus t squared, and the orders of integrations are dt and dx. So now we are interested in to reverse the order of integration. But to do so, we need to estimate t and x. So let's make an observation. We know that both t and x are between 0 and 1. And we know that t runs from 0 to x. Therefore, t is less or equal than x. And both are between 0 and 1. Therefore, t is greater or equal than 0 and x is less or equal than 1. So this allows us to reverse the order of integration and also to adjust the integration limits. So the outer one is from 0 to 1, the inner one runs from t to 1, and then we have 1 over x times square root of 1 minus t squared, and the reversed integration order, which is dx dt. Now we have a product which we can integrate separately. The first one is the integral from t to 1 of 1 over x with respect to x. This gives us natural log of 1 minus natural log of t. And we know that natural log of 1 is 0, therefore we have minus natural log of t. Now we can plug that into our integral and get the integral from 0 to 1. And the minus of natural log we can multiply to our integral. Then we have natural log of t divided by square root of 1 minus t squared dt. And we see that we have a square root of 1 minus t squared. This has the form a squared minus t squared, where a is a fixed constant and t is a variable. Whenever you see this, you need to substitute t by a times sine of y, let's say y. And let us substitute t by sine of y. So a is in our case 1, so therefore t is equal sine of y. Then dt is just cosine of y dy. And also the square root of 1 minus t squared. T is now sine of y, which gives us sine of y squared. This is equal to cosine of y. All right, let's plug them into our integral. And we get minus the integral of natural log of sine of y divided by cosine y. And dt is just cosine dy, cosine of y dy. And we see that 1 over cosine of y will cancel cosine of y. And we need to calculate the bounds. So we see that if t equals 0, then sine of y is going to be 0 as well. If t equals 1, then we have that 1 equals sine of y, then y is going to be pi over 2. And we are left with the integral from 0 to pi over 2 of natural log of sine of y dy. And don't forget the minus here. Okay, this is now an important result, and we'll integrate that in the next step. Alright, so far we found out that our initial integral is equal to minus the integral from 0 to pi over 2 of natural log of sine of y dy. For simplicity, let's consider the positive part of this integral, which you can denote as j. So j is equal to the integral from 0 to pi over 2 of natural log of sine of y dy. And this is actually a tricky integral to solve, and the usual methods, for example, integrating by parts or UV substitution, will probably fail. So we have to come up with a new solution. And there is the so-called King's rule for definite integrals, which state that the integral from b to a of f of x is equal to the integral from b to a of f of a plus b minus x. So let's try to apply this King's rule to our integral. Then we get by the King's rule, the integral from 0 to pi over 2 of natural log of sine of, now we can plug the limits into our sine. Well, a associates with our pi over 2, then we have sine of pi over 2. B associates with the 0, then we have pi over 2 plus 0, that gives us pi over 2, minus x associates with our y angle, then we get minus y dy. And we know that sine of pi over 2 minus y is the identity of cosine of that angle. So then we get the integral from 0 to pi over 2 of natural log of cosine of y dy. So how did this help us to solve our problem? Because we started with natural log of sine of y and we ended up with something really similar. At this point, I want to illustrate the graph of these two functions. So let's draw coordinate system. And we are observing the functions from 0 to pi. Let's say pi is here. And this is the graph of a sine function, where sine takes its highest value, which is at 1. Sine takes it by pi over 2. And if you take the natural log of sine, then we know that sine attains values between 0 and 1. And we also know that if you plug in values between 0 and 1 in natural log, then you get negative values. Where for 0, you have a divergence towards minus infinity. So let's try to plug that into natural log. Then it would look like something like this. Where at this point, it has an asymptotic behavior. Then we are interested into calculating this area, right? And the cosine function is going to, let me get a different color. The cosine looks something like this. And if cosine of 0 is 1, then we know that this is the only root of its natural log. So then we start here, and we have an asymptotic behavior by pi over 2. All right, and then we are interested into this area. So the blue and the black areas are actually the same. So then maybe we can try to combine both in an additive way, because it's really tempting, because you see that we have natural log over here and natural log over there. And if we have sum of natural logs, then we maybe can make use of some natural logs property. So let's try to add this integral to this integral. This will give us 2j is equal to, and since we are dealing with the same area and the same bounds, then we can take both integrands into the same integral. That gives us the integral from 0 to pi over 2 of natural log of sine of y plus natural log of cosine of y. We are integrating with respect to y. And we know that sum of logs is the same as log of product. Then we can rewrite this as the integral from 0 to pi over 2 of natural log of sine of y times cosine of y. Then by a trigonometric identity, we know that the product of sine of y with cosine of y is equal to the sine of 2y divided by 2. So let's try to plug that into our integral. Then we get the integral from 0 to pi over 2 of natural log of sine of 2y divided by 2. And we know that log of product is the same as the sum of logs. Therefore, we get the integral from 0 to pi over 2 of natural log of sine of 2y plus the integral from 0 to pi over 2 of natural log of 1 over 2. Alright, as a summary, we started integrating the arcsine of x divided by x from 0 to 1, and then we found out that this is the same as minus the integral from 0 to pi over 2 of natural log of sine of y, and we ended up getting 2 times j is equal to the integral from 0 to pi over 2 of natural log of sine of 2y dy plus the integral from 0 to 1 of natural log of 1 over 2 with respect to y. So, and notice that we replaced I with minus j for simplicities, and let's calculate the simpler integral from this sum. And since natural log of 1 over 2 is a constant with respect to y, then we just get pi over 2 times natural log of 1 over 2. Alright, let's calculate the first integral. We have the integral from 0 to pi over 2 of natural log of sine of 2y dy. Alright, to solve this, we substitute 2y. So let u be 2y, then du is equal to 2 times dy, and dy is just du over 2. So let's substitute that into the integral. This gives us the integral of natural log of sine of u. Then dy is 1 over 2, which is a constant, so we can multiply it in our integral, and du. And the bounds are going to be if y equals 0, then the lower bound is also going to be 0, and if y equals pi over 2, then 2 times pi over 2 gives us just pi. So we end up with this integral from 0 to pi of natural log of sine of u. And since sine of u in the integral from 0 to pi is symmetric around the midpoint, which is pi over 2, then we can express these integrals in terms of half of the distance of this integral, which is from 0 to pi over 2, and we have to take the double of this integral, which gives us 2 times 1 over 2, which is just 1, and we have natural log of sine of u du. And notice how this is similar to our integral called j, right? Which is the positive part of the integral I. That is just the integral from 0 to pi over 2 of natural log of sine of y. And since u is just a dummy variable, we can replace it with y. Then we get that this is just equal to j. Let's plug that into this equality, which is 2 times j is equal to just j plus pi over 2 times natural log of 1 over 2, and we can subtract j, then we get j is equal to pi over 2 times natural log of 1 over 2, and we have to multiply this by minus 1 to get our initial integral, which was I. So I is equal to pi over 2 times natural log of 1 over 2 Or in other words, this is the same as minus pi root 2 times natural log of 2. Thank you for watching.